So welcome everybody to our class. What I'm going to do something a little different today. I gave you my videos on the 7 holy steps of subnetting, and also where I went over an older chapter on subnetting, on IP addressing, which still is very relevant today because it's not like it's changed, other than the fact that we now use more VLSM than we do anything else. But what I want to do is just talk a minute about a very important concept that is important for your students to know, and that is that IP addresses all consist of a network portion, an optional subnetwork portion, and then a host portion. And the important thing for you to remember is that the host portion cannot be all ones or all zeros for a valid IP address. So when you look at the host portion of an address, you need to be able to say, is this valid or not? Well, you have to compare it to the subnet mask, or otherwise you don't know. So for instance, I'm gonna pull up my whiteboard here and bring it over. So you can see some of my lovely handwriting for today. So let's take, if I give you the IP address 172.16.0.255, and I ask you, is that a valid IP address? You really can't answer that. You can't say it's valid or not because you don't have a mask which tells you what portion of it is the network portion and what portion is the host portion. Now, if I do this, if I say /16, now, and I ask you, is this a valid IP address to be assigned to a host? I see everybody, that's my answer in chat. I got to pull my chat out here so I can see it. Oh. Come on now, chat. I got a yep. Okay, you got to factor them in at 3:30. That's fine. Okay, same with Demetrius. That's no problem at all. Okay, so we got 2 yeses. It is definitely usable because if you look at this, we can see the first 2 octets are network bits. Okay, golly, I didn't want that. Sometimes it doesn't. And then the last 2 octets are our host bits. Now here's something interesting. Can you assign this address to a host? The answer would be yes, because not all of the host bits are zeros and not all of the host bits are ones. You've got 8 zeros and you got 8 ones. So that's a valid IP address. If I come in here and do this, okay, as soon as I do this, completely different answer.
Yeah, because it's even.
Correct. Now what you've got is 24 bits that are network bits, and then all your host bits are now ones. You can't have all host bits ones or all host bits zero. So the definition of a usable IP address is usable IPs cannot have all ones, oops, there I go doing it again, all ones or zeros in the host portion. Golly, I keep hitting that button by mistake. Okay, in the host portion. So be aware of that. That's something that gets you in trouble sometimes. I could put down, again, I could go 10.0.0.255, and you can't tell me whether or not that is a valid IP address unless I
You're muted, Kelly.
oops, I meant to turn my video off. I said, with a /8 mask, this is a valid IP address. With a /16, it's a valid IP address. With a /24, it is not a valid IP address to put on a host. So you have to look at the addresses and the actual mask associated with that address to figure out whether or not it's a usable address. Questions about that? Questions about IP addresses and their usability or their format? The fact that there's multiple. When you look at an IP address, one of the things we have to look at, there's a network portion and there's a host portion. What does a subnet mask put in the network portion of the IP address? What does the subnet mask, we're getting ready to go over that next, but what does the subnet mask put in the network and subnetwork portion of an IP address? Ones, puts ones. Puts zeros in the host portion. So looking at this right here, I can tell you the mask they are associating with this address is 255.255.255.0, because they are saying that the first 3 octets are the network portion and the final octet is the host portion. So as we look at subnet mask, they're telling us through the ANDing process what network a particular PC or device is on. So again, here we have all ones that will be in the network portion or the subnetwork portion, and all zeros in the host portion. And the only way to know what actual an IP address is valid or not, or what address it is and what network it's on, is by looking at its associated subnet mask, which is also sometimes called the prefix length. And by that, it means the number of ones turned on in the subnet mask. So if it's a /8, it's 255.0.0.0. /16 all the way down to /30. And you can see here where that will show you your mask and prefix length. That's how they're related to one another. Your host will always use a ANDing process to find out what network they're on. So if the host 192.168.10.10 wanted to find out what network it was on, it would take its subnet mask. See, going back up here, right here's it's 192.168.10.10 with its mask of 255.255.255.0, and it would AND it to that mask to determine that this host is on the network 192.168.10.0. You'll notice what it does is it leaves all zeros in the host portion of the address. If you want the broadcast for this network, what do you put in the host portion of the address? Anybody? Uzma, what would you put?
Well, in the host portion, I believe you put it'd have to be a 1.
1, correct. So in other words, this is the network address of 192.168.10.0, the network address. The broadcast for that network is 192.168.10.255, because you put all ones in the host portion. By the way, if you ever wondered where I pulled that 2 to the H minus 2 from, when we talk about, there's a formula that I mentioned in my different lectures. 2 to the H minus 2 equals the number of usable hosts on a network. Okay, so the number of usable hosts on a network. So even using a simple network of 192.168.12.0/24. Okay, so the formula is 2 to the H. So there's 8 bits. So 2 to the 8th minus 2 equals 254 usable hosts, even though there's 256 positions here. The reason for that is because the first usable address is .1, the last usable address is .254. You can't use the address, can't use 12.0 to put it on a host because the host portion is all zeros. That's the network ID. And you can't use 255 for a host because that is all ones in the host portion, which is the broadcast ID. So the final address in every network is a broadcast, and the first one is actually the network or the subnetwork ID. So if you ever wondered where those 2 addresses were going, that's where they're going. They're going to be the network ID and they're going to be the broadcast ID.
Kelly.
Yes, sir.
How beneficial is it to teach the class like a math class for the exam? I mean, would they need to, will any questions be phrased like this?
What they will probably give you is this. They will say, all right, given the address 192.168.12.32/27, can that address be assigned to a host? Okay. Now, the way to determine that is this. /27, what you know that by no doubt, these first 3 octets are all network bits, right? We know that for a fact, okay? We borrowed 3 bits. So what we have to do now is we have to take this 32 and convert it to binary. So 128, 64, 32, 16, 8, 4, 2, 1. We borrowed 3 bits because we're /27. So we're over here in our third octet. So these are our subnetwork bits. Now take a look now. What's wrong with this address? Why can't I put it on a host? These are the host bits.
No ones.
Well, these are the host bits. And guess what they are? They're all zeros. So 192.168.12.32 is actually the subnet ID for the 32 subnet with /27. If I gave you a different address, if I gave you 33 though, watch what happens. Changes completely because now this is a 1. That's a valid address to put on a host because all the host bits aren't 1s, all the host bits aren't 0s. So you don't really need to teach them a math class, but you do need to teach them the ability to look at a mask, compare it to an address, and see if that's a valuable or a valid IP address. Let me give you another good example here. Let me give you another one to look at. Let's try this. Let's try, what if I gave you 10.0.33.255 slash, let's see, 8 and 8, 16, 19, okay? First off, what is a mask of /19? We got 255, that's 8 bits. 255, 8 bits is 16. Now we got to have 3 more bits turned on, right? So 1, 2, 3 here. So it'll be 224.0. That should be our new mask with a /19. So we know off the bat, these are network bits, or at least subnetwork bits. Okay, no doubt. So we need to figure out, are all what's left of these host bits, are they all 1s, or are they all 0s? So we'll go in here now, we'll take 33 and convert it. So 1, 28, 64, 32, 16, 8, 4, 2, 1, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we got 19. So we got 3 more bits here that are going to be our subnetwork bits. We come right here. So there's our host. This is our network bits. These are our subnetwork bits. And now we're left with all of these other bits right here. Are they all 1s?
No.
Are they all 0s?
No.
Valid IP address to be placed on a host. Okay. Here's another type question you might get. The very same question you may get out of this. You may be asked, what network what network is this address on? So what subnetwork is this address on? How would you find that? What's the correct way to do it?
Bit count.
Okay, bit count. Well, the easiest thing to do, honestly, is just AND it.
Yeah.
So let's just go through the ANDing process. Because remember, if you AND this IP address with this mask, the network's going to fall through. So the first off, I can tell you unequivocally, if I AND 255, 255, 255.224, if I AND that, this is going to fall through, I promise you. So 192.168.12 is going to fall through. I can basically ignore that because I know that's going to fall through. Now let's convert 230 to binary. So let's see here. We got to do, what's the method for conversion, by the way? What's the method if I want to convert a decimal to binary? So I got 230.
Yeah, subtract.
Subtract. So I take 128 away from it. So I can turn that on, which should leave me with, see, there's 2, there's 1, that's 2, 0, 102, right?
Yep.
Can I subtract 64 from that?
Yep.
Yep. So 64 here, that becomes 9, that's 8, 6 9 is 38. So that gets turned on. Now, next one is, can I subtract 32? Yep. I can. 32, which leaves me with 6. Okay, so that's 32, 16, 8, 4, 2, 1, right?
Correct.
Now, I'll show you an easy thing you could have done to make this life a lot easier. Remember, if you have 1, 1, 1 and all zeros, it's 224. you could have started with by subtracting 224 with a remainder of 6. Turn the first 3 on and it tells you've got 6 left. All right.
Yeah.
But,
Kelly, in
yeah.
my experience, I always have to give my students a little cheat sheet where they do their binary first to know what's on or off.
Right.
And then they, put their bits out there, because sometimes that was the obstacle.
Oh, you're talking about doing this like 2 to the 0, 2 to
Yeah,
the 1?
yeah.
Yeah, I tell you, anytime I take a certification exam, the very first thing I do on that little grease sheet I have is I write out 2 to the 0 down to about 2 to the 14th.
Yes.
Because if I don't, I'll make a dumb mistake. And so I completely agree with that. I usually do that all the way down. Then that way they can very easily see. But now what we do is we've got /27. So we go 1, 2, 3, 4, 5, 6, 7, 8. All right. So we're going to do this. And we'll see what falls through here is 1, 2, 3, 4, 5, 6, 7, 8. And that is 224. So this host 192.168.12.230/27 is on the network 192.168.12.224. So you can AND to the mask to find out whatever network or subnet any address is on. Now, Benjamin, that's the level of math you got to get your students to. So it's a good understanding of converting from binary to decimal, decimal to binary, and a good understanding of the values of each position, which, like you said, this 2 to 0, 2 to the 1, 2 to the 2, all the way down 2 to the 3, so on and so forth. Does that help everybody?
It worked well. I give them that, and I give them a little chart to help with their conversion, because like some of the others, some of my students aren't what you would consider traditional college students.
Right. Well, and the other thing, folks, I've got 2 degrees in English, so if I can do the math, it's not that hard. And I do mess it up. Like I said, you noticed I actually messed up. If you watched one of my videos where I was doing some subnetting the other day, I totally blew it. I actually overlapped some stuff in one of my Thursday meetings. So we do make mistakes. We just try to minimize those mistakes as much as possible. But yeah, the only thing I will tell you is this. I like charts. I like charts for being able to subnet in the real world. What you've got to be very careful with is to remember your students can't carry those charts into the test. So you've got to teach them a method that they're going to be able to reproduce when they're sitting with just a grease board in front of them taking the CCNA exam, or they're sitting in front of someone who's interviewing them for a job interview, and they asked them to do a subnetting. If they don't have that chart and they're unable to subnet, that's going to be detrimental for them to get that job, with no doubt. Now, real world, we all check it with a subnet calculator. Let's be honest. I mean, I'm not going to build out a network and not check my work against a subnet calculator. That would just be insane. But if I was in a job interview and asked, I would have a process to be able to do it in person and say, now, once I did this, by the way, I would go and check it against a subnet calculator and make sure I did it right.
Now, what's interesting is that you guys, like I've taught a digital logic class, and I've never used a subtraction method before, but that seems so much easier than just the, I normally do the division by 2s, and so it's a little slower process.
Right. And the subtraction method, again, is very, very simple. And just remember, if you're going the other way, if you've got the binary, 1, 2, 3, 4, 5, 6, 7, 8, you just do the addition method. So it's 128 plus 64, 32 plus 16 plus 8. And so you can go from there and do the addition method to get your decimal values there. And again, one of the things I do teach my students is, these breakpoints. So 1 and all zeros, 128, 1, 2, 3, 4, 5, 6, 7, 8, 1 and 6 zeros. So this is 128. This is 192. 1, 2, 3, 4, 5, 6, 7, 8 equals 224. 1, 2, 3, 4, 5, 6, 7, 8 I wish I had $1 for every single time I put a 1 and a 0 on a board. I'd have about at least $100. 6, 7, 8.
Yeah. So I normally do the division by 16 or 2 and either convert from hexy to binary but I like the subtraction method there as well too.
And that is also mathematically a viable method. And honestly, some of your strong math students may prefer that method to the addition subtraction methods, or to the subtraction method. But you know, I tell people all the time, there's multiple ways to do this. You've got to find the one that works best for your students. And I like to introduce them to as many methods as possible so that they also have, can find the one that works best for them. So.
Actually, I agree. I also do teach digital logic, and I try to introduce them to at least 2 methods on going back and forth. And I found that it helps and allow them to choose the method of preference. And I prefer for them to do the chart before they start doing anything. But I'd never done the chart like you just did. I think that's another tidbit that I will use now moving forward, where I can lay the last chart you just did.
Yeah, the ones with the 1 and 7 zeros is 128 and 192. Yeah, if you can learn those breakpoints, that really helps with your conversions. The other thing I always do stress too is make sure they remember, you know, no matter what the number is, 4, 5, 6, 7, 8. If that final bit position is on, it's an odd number. If it's off, it's an even number.
Yeah.
And so that helps. Go ahead.
And Kelly, sometimes I try to help them practice creating their cheat sheet so that when they go to take the exam, they can create it there and then of everything that they need, so they don't have to worry, you know.
Yeah, and that is a wonderful idea. That is, I think one of the things we fail, and I fail miserably too, is in actually preparing the students to go take that test. Taking certification tests is a skill. I mean, it really is. It is a skill you learn. I remember when I took the very first exam I ever took was way, probably before Benjamin was born. It was Networking Essentials. And I was more afraid of that test than I was to sit in front of the group that reviewed my master's thesis for my English degree. You know, it was just, I was that scared of it. So there's definitely a technique to it. And if you can help them build that, you know, tell them, like I said, that put that chart out there. Anything else they need to remember, you know, it's fine to write over here on the other side. If you want to put out your application, presentation, session, transport, you know, until you click start on the exam, you know, network, data link, until you click start on the exam, your time doesn't start. Now, within reason, you can't sit in there and transcribe for 47 days before you start the exam because the test center is going to get mad. But you can create a decent little cheat sheet there, and that's not cheating because you're bringing it out of your brain. That's just preparing yourself to make sure you don't make a silly mistake during the exam.
And that's one of the reasons that from my experience, what I found with my students, when I teach them to do the magic number, well, I'll put that label on it for lack of a better term.
Right.
Where I go from 1 and, you know, 2, 4, all the way up on the chart, and then they can just do your bit marks underneath it.
Right.
Because it's simple for them to remember 1 to 128 and put your positions in there, and then you can convert it either way.
Definitely. Yeah, excellent. Very good. Any questions about the difference between a network address? Remember, network addresses have all zeros in the host portion. A broadcast address has all ones in the host portion, and then a host address has neither all ones or all zeros. So a host address is a usable IP address that can be assigned to a host. And that's all they're showing you here. Network address is all zeros. Broadcast is all ones. Anything that's not all ones or all zeros, completely usable for a host. Okay. So I like this where you can just go through and AND to your heart's delight. So if you have students having trouble with ANDing, just continuously brings out new questions. So you're able to have them do that if you need some testing or a way for them to work on it, which is nice to have that built into the curriculum like that. We're going to talk just a second about unicast address. Unicasts are 1-to-1, so it's a singular IP address. So 4.1 to 4.253, that would be from one source to one destination. Broadcast is 1-to-all. Anytime there's a all ones destination, that is a broadcast. So in this case, this is literally every single device would have to look at this up to at least layer 3. And then you got what's called a multicast, which is 1-to-some. So it's 1 to those who join a special multicast group. In this case, indicated by 224, which is the old class D addresses, 224 to 239. Okay, any questions about those? We don't deal a lot with multicast in this class, although they show you here that 224.0.0.5 is the all OSPF routers. And then 224.0.0.6, you'll learn is actually all designated routers in OSPF, which is a special form of OSPF router.
And I assume it may, if someone want to do a special project in streaming, then you may want to look at that, right?
Definitely, yes. In streaming, stock tickers, things of that nature. So let's imagine that only the host, let's say the 2 laptops, they were the only 2 hosts that wanted to get a continuous stock streaming app sent to their desktop. You would have them join a multicast group. And then when that multicast went out, even though it would go to everybody, only those hosts that are part of that multicast group would actually bring it in and deal with it. They actually, because they have that multicast, they create themselves a special MAC address that's part of the multicast group, which allows them to bring that in, look at it at layer 2, pass it up to layer 3, see it at layer 3, and then pass it on up to the application layer. So yes, that is a great example of how multicast is used. All right. So types of IPv4 addresses, just real quickly, if you're ever at a party and someone says, oh, what do you know about RFC 1918 addresses? I always use this fictional dinner party, kind of like in Harry Potter when they invite people to have the big party and talk about important and interesting things. Well, RFC 1918 are the private address blocks, and it's basically the 10 network /8, 172.16 to 172.31, and then 192.168.0.0. These are all non-routable on the internet addresses. So they are designed to be used internally, any way you want to use them internally, and they will route internally, but you will then have to NAT them to public addresses. So these will not go out on the internet. In fact, almost all ISPs have an access control list that is designed to block these addresses from going onto their networks. To route on the internet, you're going to have a public address. And to do that, your ISP or at your border, you will have to translate from a private RFC 1918 address to a public address. Now, the bad news is all public IPv4 addresses are pretty much gone. So at this point, there are some parts of the world where, like in India, some of the traffic in India is being NATed 6 or 7 times before it actually becomes a public address. So that's why there are other parts of the world that are more quickly adopting IPv6 than we are, because they're so deep into NAT due to the number of people using the internet. Then we have a couple other special use IP addresses, such as 127.0.0.1, which is our loopback, also : 1, which is a loopback for IPv6. And then this is something that came out. They call them link local addresses now. I call them a PIPA, automatic private IP addressing. The funny thing is when this first came out in Windows, I believe it was Windows 91 flavor of 95 or 7, they really didn't advertise it. And so what happens is when a Windows machine boots up and doesn't find a DHCP server, it gives itself an automatic private IP address in the range of 169.254.0.0/16. Well, even Xboxes will do this now. All Microsoft devices will do this. And so it became kind of like a de facto link local IPv4 address, which is only usable on that one segment. but they didn't tell us about it. And so I was out looking for somebody who had a rogue DHCP server that was giving out 169.254s. And then finally did a little research that, oh, okay, that's what's going on. But if you ever see that your machines have got 169.254 addresses and they're supposed to be getting their IP addresses via DHCP, which is Dynamic Host Configuration Protocol, or dynamically, more than likely your DHCP server is inaccessible or has run out of IP addresses to give out.
Or your cable's not connected.
Well, if the cable's not connected, it won't give itself anything at all because it doesn't have layer 1, layer 2 connectivity. But now your DHCP servers cable could be disconnected. Yeah, that's a good point. Very good point.
Hey, Kelly, how much are IPs nowadays?
I don't even think you can't buy them.
How do you get them?
What happens now is actually many ISPs are actually running private addressing inside a part of their networks so that you're not getting natted until you leave the ISP. And so ISPs they're doing some really weird things to work with the addresses they've got. I don't know anybody who's bought or been able to purchase an IPv4 address anytime recently. It's a crazy story. We used to have a Class C here, a true Class C that we owned. And I tried to get them to keep it and they wouldn't, which being a good internet citizen, it was good to give it back. But I wish we would have kept it. Honestly, Benjamin, I don't know. I've not tried to buy one anytime recently. And I don't know that you can even easily buy one. Now you can get them from your ISPs. They will give you public addresses. But typically it's only with a business account and it's at a certain service level agreement that they're giving them to you.
Yeah, you will pay a premium for it.
Yeah, if you want your own public IP address, you would definitely pay premiums. Universities are a little bit like us in the community college system. The community college system was able to garner a fairly large amount of addresses, actual public addresses, and then they've handed those out to the community colleges in the state of North Carolina, and they control it. So it depends on, and the university system, I'm sure, is the same way in North Carolina. But it's very difficult to get one this day and age. Now, this is something I want to talk a good amount about. I teach my students classful subnetting. Now, back in the old days, and a lot of people talk about classful, you'll see here there are roughly 5 classes. There's class A, B, C, and D. D was the multicast block, E was an experimental block. But the ones that we know mostly are class A, B, and C. And you will see that they were the class A's were the 0 to 127. And remember, they pulled the whole 127 network out /8 to be loopbacks, which is a little bit crazy, but they did it. Okay. But 0 to 127 is all a class A. And one of the things I want to do here is let me pull up this whiteboard again. Let me make a new whiteboard because I want to show, pull this here. I want to pull this over here because I want to show this. All right. So with a class A, have you ever wondered why it is 0 to 127 for a class A? Anybody ever wondered why it was that? The reason being is in the first octet of all class A's, the first bit position has to be a 0. So if you think about 1, 2, 3, 4, 5, 6, 7, 8, that is 0, obviously, to 0, 1, 2, 3, 4, 5, 6, 7, 8. That's 127. That's how they got the class A range. Okay, now, get rid of all these because it won't get rid of my 0 there if I don't. Oops. You also know that from class A, the class A's follow a format. Since it's a /8, class A's have a default mask. The mask on a class A by default is a /8, which is 255.0.0.0, which is a format of network.host.host.host. In other words, there's 8 network bits and 24 host bits. But you will read that there's only 128 total networks available. But why when there's 8 bits? That is because the first bit always has to be a 0. So you really don't have all 8 bits, you only have 7 bits. What's 2 to the 7th? 128. Okay, so that's a class A. That's the range, the first bit, and the first bit positions, the mask, and then the format here. Okay. Now for a class B, the range is 128 to 191. The first 2 bits have to be a 10. The mask is /16, which is 255.255.0.0, which gives us a net host. Okay, you don't need that last dot there, but ignore my last dot. Net host, which is 16,384 networks, which is confusing because there's 16 bits, but remember 2 of those bits are reserved because they have to be 1 zeros. So 2 to the 14th is 16,384 total networks. So if you ever wonder why it's not 65,534 networks and 65,534 hosts, it's because you have to reserve those first 2 bits to be a 10 for it to be a class B.
And that goes back to that formula you gave earlier, right?
Exactly.
Okay.
Yep. For the host portion, it does. That's why you got 65,534, because 2 to the 16th is actually 65,536 minus 2. Class C is 192 to 223. The first bits have to be 110. It is a /24, which is the standard mask, which is 255.255.0, or net, and then host. Okay. In that case, you've got 2,097,152 networks of 254 usable hosts, because you got 8 host bits, and that's what we were talking about. 2 to the H minus 2 equals number of usable hosts. And we've got 2 to the 8, 256 minus 2 is 254 usable hosts. Now, for the longest time, we used these class of addresses, and every time we would put networks together, or we would subnet. So if we had a router here, we had it connected directly to a router here, and we had that connected to switches here, okay, and a switch here. All right. Every network would have the same mask. So in other words, we would have over here, say 192.168.13.0/24. This would be 192.168.12.0/24 for this network right here. And then this might be 11.0/24 over here. Again, 192.168.11.0. But with classful addressing, the same mask was used for all subnets and all networks. The lecture that I give you here and my description of the 7 holy steps of subnetting is only good for classful subnetting. The curriculum doesn't even really teach classful subnetting. It does a little bit, but not much. So if I go down here and we look at, we go down here and looking at subnetting, reasons for subnetting, we'll get back to that. But basically, if I subnet along a boundary, okay, so it is possible to subnet along a boundary and do it so that you're using the same mask on every single portion, okay? So you can do that. That's classful. That would be classful subnetting. The thing that we do now, though, is we typically don't use standard classful subnetting. I like to teach it, however, because I like to show students why classful subnetting has problems. So I'm gonna go ahead just real quickly. Questions about these different types of addresses, these classful addresses. You understand now how we got, by the way, class D, 224 to 239, 1110, and then 240, 255, 11110. That's how we got those. That's how they come up with those ranges. Okay,
I have a question.
Go
I
ahead.
wonder that this class A that he said that the host is like up to like a 60 millions.
Yep.
I wonder what kind of a company or organization have that class A subnet?
Xerox,
Uh,
Ford,
Xerox,
GE.
Ford, the military, because remember, it's 16 million devices.
Okay.
But now here's the very, very important point you just made, Dr. Hugh. That is not a very useful network. Okay. Let's be honest. If I tried to do this, if I tried to take and build a network and I tried to make this one network a class A, so there's 16 million hosts hanging off of gig 00 of R1, you would have so many problems with broadcast, so many problems with networking issues, it would not work.
It doesn't scale.
It doesn't scale at all. Exactly. So what we have to do is we have to take those networks and that big network and we have to subnet it. Now, I'll show you what we typically do. We know from RFC 1918, so RFC 1918, we know that 10.0.0.0/8 is a private address, right? Non-routable. Okay. So let's imagine this is our school at Stanley Community College. Here's what you can do. You can subnet this. Now let's imagine first we're going to subnet it. This is literally one network of 16 million plus hosts. Okay, pretty much useless. But let's imagine if we borrow 16 bits and suddenly we now have these subnets. All the way down to, and by the way, it will go on until you have 2 to the 16th networks. Okay. But now notice what I did was I took this huge network, one network of 16 million hosts. And I now have created, by the way, I borrowed 16 bits. So it's 2 to the 16th equals the number of subnets. Okay. Which is what, 16 million and change, 16,776,000 networks. So I could go all the way down. By the way, the last usable network here would be, if I do my math right, would be 10.255.255.0/24. Okay. So I'd go all the way down to that. But what I can do now, each one of these networks, how many hosts are there on each one of these subnets now?
Well, there's at least God,
How many host bits have you got on this subnet right here?
24.
Nope.
200.
No, I'm sorry, 8.
You've only got 8. So each one of these subnets is 254 usable hosts now. So Dr. Hugh, you're exactly right. This network right here is pretty much useless the way it is. As one network, as one network of 16 million hosts, we really can't apply that to our networks. But if we borrow it, if we subnet it, and we start borrowing host bits, by the way, subnetting by the definition, if you ever at that dinner party and somebody walks up and says, hey, do you know what subnetting is? Well, subnetting is the process of borrowing host bits to increase the number of network bits. The number of, network bits. Because you'll notice what we had before, when we have a normal class A, we have 8. Right now, we've got, with a /8, we've got 8 network bits. We got 24 host bits, right? That's what we got here. Well, golly, I did it again. With this down here, we've got 8 network bits. We have 16 subnetwork bits, and we have 8 host bits. And that became a much more usable network because 254 hosts in a broadcast domain, that's not unreasonable. That's not unscalable either. But the beauty is now we could take this and I could take one of the buildings at Stanley Community College. So we could take and say that Whitley Technology Center, the building room 112 is going to have the IP address of 10.0.112.0/24, and all the hosts in that room will have that IP address. Room 113 would have 113.0/24, so on and so forth, so that I could take this one huge network and break it down. That is by definition the whole reason we subnet, because we don't want these huge broadcast domains. We want smaller broadcast domains. In fact, the smaller the broadcast domain, the better, but you just have to be careful because each broadcast domain has to have a routed port that routes between it.
But that also adds a collision domain for us as well, which helps.
Correct. It adds a collision domain, which helps us. Now, I will say this, in a modern switch network, you should never have a collision. Should not happen. There should be no collisions in a modern network. Do they happen? Yes, but typically it's because of misconfigurations due to running cables too long or a NIC failing or something of that nature. We should not have collisions in a modern network.
Okay.
Other reasons for segmenting, one is location, just like I talked about in my example. We could take and subnet by room so that each room is a separate subnet so that traffic is separate from one another. We could do it by group or function. So you could put administrators together. You could put human resources, students, accounting. You could do it by group or function. Sometimes we do it for security reasons. So in other words, we put instructors in one VLAN. We put students in another VLAN so the students can't access the instructor's machines and try to get things off of those machines. You can do it by device type. Like for instance, a great example of this is your wireless network is a different subnet or different network than your wired network, so that you can track the wired clients and wireless clients separately.
Kelly.
Yes.
In the future, do you ever see the incorporation of the containers and Kubernetes in these diagrams?
Yes, most definitely. Yeah. You could have, in fact, you could already have that. You could very easily, you've got this diagram right here. There's absolutely no reason. In fact, let me show you. Let me do something here. I can show you kind of something to be a cool idea here. I'm grabbing this image out of here so I can stick it in the whiteboard. So let's imagine we've got this network right here, which is all fine and dandy. Let's zoom in on it a little bit so we can see it better. But then let's imagine that we've actually off of here, okay, we've got a server. All right. Golly, that's terrible. So we got a server here, and this server is a virtualization server running containers. So you got a vSwitch in here, right? So in here's what's called a vSwitch. I'm gonna zoom out just a little bit, so I got a little bit. So you got a vSwitch in here, which is a virtual switch. Okay, so there's a switch in here. Well, inside of here now, you could have an entire subnet that is 10.0.5.0/24. And this could be all your containers that have, give you a great example. Imagine this is containers holding packet tracer pods or whatever you want. This could be your Bitcoin mining containers or whatever. You could have a subnet in here that's connected to this vSwitch, and all the containers are right in here and have a 10.0.50 number. So you can separate them just like that. Because all it becomes is another network on your network. It just happens to be that instead off of a physical switch, it's off of a vSwitch, which is called a virtualized switch inside of ESXi or inside of Azure or inside of AWS. Any of those, it can do it. Because you can have your a lot of people, like in the cloud, like if you're in Azure, and let's imagine this is an Azure cloud here, and you've got your VMs in this Azure cloud. So this is all VMs here. So these are VMs. Well, those VMs have to get to the real world somehow. So the Azure cloud has a vSwitch. And that vSwitch connects to a real physical switch. And that real physical switch hits a router somewhere. And so these things are coming into that virtual switch, and that can be, you can subnet your containers any way you want to. Does that help, Benjamin? Does that make sense?
Yes, that's excellent. Excellent.
In fact, that's we do that right now inside of our all of our networks. We have multiple different inside subnets that we use for our virtualization components.
I have another question.
Okay.
Here, so you use the address 10.0.0 or like a 172 or 192 because then those are mostly private address there. Now, for subnet. Now, is that, I mean, possible, or does that make sense to use the IP address like 11.0.0, instead of that private network for subnet? For example, like for on our ASU campus, we use 10.0.0 as subnet, or sometimes 192. Now, I never saw that anybody use 11.0.0 as subnet, for example.
The reason being is because somebody owns this.
Oh, okay.
This is a public address. Okay. So somebody owns that address, and it is routable somewhere in the world. We can look it up. We can go to ICANN and actually look up 11.0.0.0 and find out who owns 11.0.0.0.
So we don't use it, for example, let's say on ASU campus for a room, for example, use 11. Something as subnet. We don't use that.
You don't use it, right? Because it's owned. In fact, right here's who owns it. The 11 network is owned by the Department of Defense.
Okay. All right.
And they actually, they own this since 1984.
Okay.
So that's why, in fact, that's why you will see inside, you will only see these private addresses. You will only ever see. Now, I will tell you this. There's no rule that says you couldn't use them inside and then NAT to public addresses, but it's just bad internet form, and it's bad use because somebody else owns those addresses. It's the preferred method is to always use your private address blocks instead of anything that's public.
Okay, that makes sense.
Yeah. That's why you'll almost always see these addresses here. And the crazy thing that people don't realize is, even if let's imagine two companies merge, and those two companies, so this is company A over here, and they're using the 10 network, 10.0.0.0 over here /8 for everything inside. Well, you got another portion of the company over here. They can actually use 10.0.0.0 /8, as long as between these two, you NAT to something that's not 10. So if you NATed everything to 192.168, 12.0/24, you could do that. Now, the problem becomes when you start trying to do DNS entries and all that. So it is possible to do this. In fact, that's why if you ever deal much with Cisco's NAT, they've got inside global, inside local addresses, outside global, outside local addresses. It gets crazy. We'll talk about it when we get in the last class, in our third class. But it is possible to do this. It's just not something we do very often, simply because it can cause some headaches for your networks. But always internally, we try 99% of the time to use the private IP addresses. The negative is this: anytime you're NATing, you're breaking that end-to-end path traceability. So in other words, as soon as I NAT, there's no way to trace easily all the way down into what host sent that communication to the internet.
That's good, right?
It's good and bad. It's good if you're living in a place that they'll come and get you and carry you away if you speak against the government. It's bad if you're hacking into power grids and we're trying to track down who hacked in the power grid. So it's a double-edged sword.
Just like VPN too, though, right?
Exactly. Yeah, just like VPNs. With that, I tend to lean towards the privacy is more important, and so that's my personal stand. Everybody's got their own. I also think that for the most part, if you can get it back to the basic network, you can find most of the time who was responsible. It just becomes a little bit harder You know, there've been several we've actually had a couple cease and desist letters sent to us for people downloading movies from our network. Well, it's very hard for us to trace that all the way back to who did it, especially in a particular lab. Now we can do it easier because we have students logging in as themselves and we're tracking it. But there's arguments on both sides. I personally think it's good myself.
But because my understanding is that even with some containers that you can have them set up where they can come up, do what you need to do, and then disappear.
Exactly. And that's, you know, honestly, if I'm hacking, that's what I'm going to do. I'm gonna spin up a VM. I'm gonna spin up a VM somewhere in an Azure site or an AWS site that I've breached. I'm gonna do everything I need to do. I'm gonna exfiltrate the data and I'm gonna take it somewhere else and, you know, then spin that down and you know, it makes it much harder to track, no doubt. So one of the things we're going to continue to talk about, and I'm going to end class here in just a minute, but we're going to continue to talk about the reasons for segmenting. We want to subnet so that we can make our network small enough to be efficient. So we can subnet along the octet boundaries. So we can subnet /8/16/24. Okay, so again, here's an example of a 10.0.0.0 using a /16. So in other words, I used a /24. The example they're showing you is /16. So you could have broken it into these subnets instead of the /24s. Here it is as a /24. The other thing you can do is this. You can actually break it down into a /16 and then further break it down once you get inside of a building. So what we do, one of the things we do here, for instance, we've got the 10.0.0.0/8. Go ahead and break it down to 10.0.0/16. So it'll be to 10.0.255.255. That's a /16. And it's 10.1.0.0 to 10.1.255.255. Okay, but then you could actually take this, you'll notice you've got inside of this, you could then break this down and this could all become 10.0.1.0/24. I forgot to put 10.0, 10.0.0/24, 10.0.2.0/24, and it'd be .3, .4, .5, so on and so forth, all the way down. So I could take and break this /8 to a /16 and then use those /16s for buildings. And then inside of the buildings for every classroom, I could do /24s. And that's really what they're showing you in this example here, how you can break it down first using a /16 and then take those and break them down using /24. And you're able to, you could apply it to a building. This is a great idea because what you could end up doing, imagine, I'm going to add one more here just so I can show you this. Okay, so there's that network there. But let's imagine I have 3 buildings. Okay, so I have my central building on campus, and this building is going to be my 10.0.0.0/16 networks. And this building over here is going to be 10.1.0.0/16. And this building is going to be 10.2.0.0/16. So let's imagine that this building has 40 classrooms in it. So I'm going to have 40 subnets that are /24s over here. So I'd have, you know, 10.1.0.0/24, .2.0 all the way down to .40.0/24. But instead of having to advertise 40 networks from my routing protocol back to the core, I can summarize it as 10.1.0.
That address should be 10.1.1.0 and then 10.1.
Oh yeah, I'm sorry. You're right. Thank you. Yep, you are correct. My fault. Sorry about that. Good catch. 10.1.1.0, 10.1.2.0, and then 10.1.40. Thank you, Dr. Hugh. Thank you very much. Yeah, I was messing
No
up.
problem.
But the good news is we can take then, instead of having to advertise 40 subnets back to our core, we can advertise one network back, because all of these subnets are inside of this /16. Likewise, we can advertise one network back here. And now we have a much more efficient network, because instead of having the possibility of 80 routes in the routing table for the routers inside this core building, we literally can do it with 2 routes, one to building A, one to building B. So when we get into subnetting and we keep working on this, always think about the reason we're subnetting is to make our networks more efficient and to make them use the IP addresses we have more efficiently. Questions?
So basically, the subnet, the number of subnet is related to the number of routers or equipment used, right?
The number of subnet, yes, the number of subnets will be related to the number of different broadcast domains you want. And that is, and the way to think about it is every router port on a router is a broadcast domain. How familiar are you with layer 3 switches, Dr. Hugh?
Yeah, I used that before, but not that deeply.
Okay, well,
Yeah.
what we would do in the real world with this type of setup is out here in this building, there would be what is called a multi-layer switch, which we represent by this little thing here. So it'd be a high-speed switch. And inside of this, we would have what's called switch virtual interfaces, kind of like what we have on the 2960s. You know, when we do an interface VLAN 1, we would create all these VLANs and VLAN interfaces, you know, 1, 2, 3, up to 40. And we would use that inside of here and we would route. So every subnet is a different routed port. So let me give you an example, one quick example. And
that makes sense, yeah.
Imagine this, if we have this network, so we got a router, a router, a router. These are connected to each other. And we have switches here. So we got switches here. It's a router, it's a router, it's a router. Switch here. That's a switch. Sorry, I know I'm butchering these, but how many networks are needed? How many subnets are needed in this particular network?
3.
Okay. There's going to be a little bit more than that. You need one right here as the shared network here. Okay. You need one right here as a shared network. You need one right here, one right here, and one right here. Basically, every router port is another network. These, though, since they're shared, are 1. So it's 5. You need 5 of them.
Okay. All right.
So think about it that way. Every router port is a different subnet or network. It's also what's called a broadcast domain.
Because they have the same the IP address in the same subnet there, exactly. Right? The port of this router and the port of that router, they have this IP address in the same subnet.
Correct. So in other words,
yes,
these two right here would have to be on the same network. So if there's 192.168 12.0, now I'm wasting lots of addresses here, so just I know I'm doing it, but this would be .1/24, 12.1, and this could be 12.2/24. So it's 192.168 12.2 and 12.1. They're on the same network, so they're on a shared subnet. Correct.
Right.
And so everything down here has to be on the same network. Everything here is on the same. Everything inside of here is on the same, and everything here will be on the same network.
Okay, I understand it.
Okay. I think that is a good point for us to stop for today. Are there any questions? By the way, thank you very much for your interacting today and how well you interact with the lecture and the class, because it does help. It helps me. It helps you, I hope. But it makes lecturing a whole lot more interesting. So I do greatly appreciate you being attentive and being willing to do that. So everybody, I'm going to stop recording.